Water freezes at 0 degrees Celsius, and we call that ice, but you can have ice at any temperature below that, and the properties are different depending on what temperature the ice is. So ice is not ice is not ice. It depends on how cold the ice is.
On Titan, right, the moon of Saturn, the temperature of the ice is hundreds of degrees below 0 Fahrenheit. And so the water ice is as hard there as granite is here on this Earth. So they build mountains with it. You can see all kinds of geological features that's built with water ice.
So is it possible to get ice so hard that like a speed skater's blade wouldn't even allow it to turn? Like you would literally skid across the ice instead of skate across it?
On Earth's surface, probably not.
Okay.
But elsewhere in the universe, for sure and absolutely.
Ooh. Oh, cool.
Ooh. I love to ski and I've always wondered something. This is from Dylan, of course. Snow and ice aren't exactly the same things, and we know ice has a thin layer of water, less than the width of a bacteria, he believes, which makes ice sports possible, such as skating. Does skiing also have to do with pressure melting, or is there something else going on with snow?
Wow. The answer is both are true.
Ooh.
The snow isn't even...
First explain pressure melting. Explain that.
Well, there is a relationship where if you have more pressure on water or ice, it is more likely to melt. This is untrue for most substances, but the more you push on something, more you push on ice, the more likely it is to be able to liquefy. This is a particular property of ice which is rare amongst substances here on Earth, and that allows us to be able to do these things like skate across ice with that tiny film of water, that bacteria with film water that we talk about. Water molecule is a V-shape, right? It's got the oxygen in the middle, and it's got two hydrogens off to the side, making kind of a V. It's a polar molecule like this. And when ice freezes, it has a tendency just to touch on the hydrogen bonds. It doesn't want to just squish in, but it wants to form a hydrogen bond lattice or a crystal. And as a result, it winds up with extra space between the molecules, space that would not have existed in its ordinary liquid form.
Because water expands when it freezes, it can only exist in that expanded state as ice. If you successfully squeeze it, it cannot be squozen as ice. The only way you can squeeze it is for it to change state and then become smaller in its volume. So you're skating on the ice, the pressure forces it to turn back into water even at the lower temperature.
Wow.
That is exactly right.
We're just pulling questions out of this grab bag, and Chuck or Gary, who's got the next one?
Okay, I'll jump in. Right, Eric Varga says, hello, Dr. Tyson, Dr. Lou, but he's downgraded you, Chuck. You're now Sir Chuck. You've lost your lordship, apparently. Can you explain how Newton's 3 laws apply to the sport of curling? Are there any other laws of physics involved that play a vital role? In advance, he says, thanks.
Well, Newton's 3 laws, as most of us know, is that first law, right? An object in motion tends to stay in motion in a straight line unless acted upon by an outside force. So the guy pushing the stone forward, it's just going to keep going and going and going, and that's why you notice that it keeps going and going and going unless acted upon by an outside force. Okay? Now, the second law of motion, force is mass times
just to be clear,
acceleration.
it keeps going because the friction is very low. Otherwise, the friction would stop it. Right.
Well,
so
you are front-running me on that point, Neil. You're absolutely right. No, it's good. It's good.
Okay,
see, because you're doing exactly what scientists should be doing, right? Which is jumping in and saying, but, right? And the but is Newton's second law, which, as you know, is force is mass times acceleration. The second law requires that you wind up making sure that the friction is just right. So the amount of force and acceleration that you get, the change in direction and then the change in speed, is what you want. So those guys in the broom up front, they are quickly changing the coefficient of friction of the ice on the whole time. And therein lies the third law, Newton's third law of motion. When it reaches its destination in the curled direction it wants, it hits other stones. And for every action, there is an equal and opposite reaction. That's Newton's third law. So the stone hits the other stones that are in the scoring area, either knocks them out or pushes them a little bit. So Newton's laws of motion are involved in all stages of this exciting, thrilling, super fast, high energy sport called curling.
Yeah, man. Let me just say this. As a former janitor, curling is the best sport ever.
If you've ever gotten your brakes changed on your car, generally the front brakes wear out sooner than the rear brakes, because when you stop the car, the momentum of the car is carried more in the front wheels than in the back wheels. So Gary, that's my conduit to what you said, where if it's going forward and there's any friction slowing it down at all, that front edge is going to respond to it more significantly than the rear edge.
You've given us an
Charles,
idea.
What do you know about that? In a rear wheel car, isn't it still the front brakes that get most of the...
It varies a lot.
Wear?
Again, if you're driving
it might change
flat,
if you just move the engine to the back.
Right. Well, it depends on if you're moving on a flat surface or whether you're climbing hills. Are you stopping a lot while you're going upward or downward? You are pushing more of your mass and force forward to the front, because a car, even though it feels like a rigid body, actually has a great deal of give to it, right? A lot of springs, a lot of flexible parts to it. So it's not a dead set thing. With our typical driving in suburbia, for example, I think, Neil, you're right on. But the complexity of driving gives us all plenty of fodder or area to be right or wrong on these.
What about the Flintstone cars?
Well, you should check out Fred's heels.
Yeah.
Now, those brake pads are some serious calluses.
Quick question. Bobsledding is an awesome sport to watch. How many Gs are the bobsledders experiencing at top speed? And also, are there Zambonis for their eyes like in skating?
Oh, that's cool.
Good question.
Cool.
Yes. The answers, let's see. The Zamboni question first. There actually is a lot of grooming of bobsled runs.
Ooh.
I do not know exactly whether they drive a vehicle down.
Can you imagine?
Like a little crawler. I do not know if that's the answer. But they pour water down them. They sculpt them. There are things that are made and changed. The channels are changed. The temperature is controlled. So there is a lot going on that's Zamboni-like on a bobsled run. That's 100%.
Can I add one thing before we take a quick break? The G forces you feel have nothing to do with how fast you're moving.
Ooh.
They have to do with how fast your velocity is changing. So their biggest G forces, Charles, are going to be like when they bank the turn. Right.
A G, A G is the acceleration rate of 9.8 meters per second squared. The amount of acceleration you feel when you're in free fall near the surface of the Earth. I did a quick calculation just now in the past 30 seconds in my head. So I'm not sure if it's exactly right. You can't quote me on this. But based on what I think, how fast they're going down the hill, the angles of the turns, and the velocities and the banks and so forth, you're probably hitting at least 3 and sometimes 4 times of gravity. So 30 to 40 meters per second squared of acceleration. So 3 or 4 Gs is my top of the head answer. I'd have to go back and do more calculation to make sure that that's off my head.
Kevin the sommelier. Hello, Chuck, Cubed, and Gary. This is you're going to love the ending on this one, Neil. This is not so much a science question, but a Seinfeldian observation. Does the luge and the skeleton? Well, we'll see. Does the luge and the skeleton events just seem like a friends dare? Keep drinking up. There, I told you like that, Kevin the sommelier.
Yes,
nice one.
I am certain the luge is for crazy people.
Yeah. Oh, you can imagine someone up the top of a mountain, sat next to Chuck with an empty bottle. Says that tray over there. I could beat you to the bottom of the mountain.
On the tray.
How many of? Wait.
Wait a minute. Which one is head first?
Skeleton is head first.
That's the skeleton. Okay.
Luge is feet first.
Mm-hmm. Okay.
Yeah. I feel like luge is like safer, right?
And so, as an adult, if you're going to say, sit on this tray and go down this icy tube at 199 miles an hour, we're going to just say no. Okay?
My answer is, if you tell me to go down a tube head first at 100 plus miles an hour, my answer is, why don't you just shoot me? I'm here. Why am I going to do the work for you? Why am I doing the work for you?
Basically ice on basically a sheet of plastic at a gazillion miles an hour was one of the most fun and exhilarating and awesome things going on. And there are other people, many of them kids, but also some adults going by me, some of them faster, some of them slower. Some of them piled up at the end of the hill. It was so much fun.
Charles, you know who gets to say that? The people who didn't die.
Yeah.
There is a survivor bias, I admit.
Okay, Charles, just
survivor,
are
yeah.
some of the craziest sports, past or present, ever to be included in the Winter Olympics. The 90-meter ski jump. I am going up a really, really high tower. I am icing down a ski slope and jumping and trying to fly. Now, if that isn't crazy, then I don't know what is.